Okay, so I'm going to work problem 1 from exam number 2, spring 2017. And this is an inclined plane problem with friction. You've got a block of mass m at rest on the incline. You're told the angle theta with horizontal, the coefficients of friction, acceleration of gravity, etc. And to work the problem thoroughly, you're told to, and properly, you're told to start with a free body diagram. So let me do that. Incline of angle theta, block of mass m at rest on here. And of course you can draw this as a point particle somewhere else if you like, but I like drawing objects that look like the description. So the forces acting on this, well, there's going to be mg down, a normal force from the plane on the mass, always perpendicular to the interface, so that point's perpendicular to the plane. And since the block would tend to slide down the plane if we didn't apply any other forces along the plane, then the force of friction is going to resist that motion. It's going to be static friction in that case, and that's going to point up the plane. The problem specifically tells you to also draw the coordinate system you're going to use, and the wise choice would be to align your x-axis with the plane. The direction up or down is arbitrary, but I'll just pick down as positive x, and this will be positive y. You could do the problem properly, reversing these or reversing the directions. It's not critical, so don't worry too much about that. And you're also told in part A to resolve your forces into components along the directions of your coordinate system. Well, if I pick this coordinate system, then n lies in the y direction, force of friction's in the negative x direction. I have to resolve my force of gravity into components in my x and y direction. And you've seen this before, but let me just draw another triangle to show you how I do this. Gravity points straight down, so that's mg down. This is an angle theta of gravity with respect to, of the plane with respect to horizontal. Okay, and in order to resolve gravity into components along this plane, I have to draw a vector in this direction, and perpendicular, I have to draw a vector in this direction, and this angle is 90. And this angle is 90. So if this is theta, then this is 90 minus theta. And since this angle is also 90 degrees, then this angle must be theta. And then sine would give me opposite over hypotenuse. Remember, this is hypotenuse, so this is mg sine theta. And this side in here is mg cosine theta. So that's how I've resolved gravity into components parallel and perpendicular to the inclined plane. Okay. So now part B says to calculate the maximum angle theta. How steep could you make this angle before the block would start sliding down the inclined plane due to gravity? And what keeps it from sliding down is friction, so we'll need the force of friction. But in order to find the force of friction, I'll need to use F friction equals mu static, in this case, times n, which means I'll need the force of n. And I'll get the force of n from the sums of the forces, Newton's law, applied in the y direction. So in the y direction, we have n pointing in my positive y direction. And we have a component of gravity, mg cosine theta, here pointing in my negative y direction. That's the negative sign. Those have to sum to 0 because the mass doesn't accelerate into or away from the plane. And so from this, I've got my normal force. Normal force is mg cosine theta. If you want to stop and think about it for a moment, if theta goes to 0, if the incline is just horizontal, normal force equals mg because cosine is 1, and that should be reassuring. So having gotten this expression, I can now write down the force of friction, which I'll need later. The force of friction, it's really less than or equal to mu Sn, remember. Okay, I'm just going to write equal to mu Sn because we want the maximum angle, which means you mean the maximum force of static friction. Okay, so this then is just equal to mu S mg cosine theta will be the force of friction just before the block lets go and slides down the inclined plane. Okay. To look at that motion down the inclined plane, I need to look at the sums of the forces. Newton's law in the x direction equals mass times acceleration. In the x direction, we have a component of gravity, mg sine theta. And we have the force of friction resisting that motion in the negative x direction. And so that's minus the force of friction, and I can now plug in for the force of friction what I have above. So we have mg sine theta for gravity minus mu s mg cosine theta. Okay, and what I really want for this is to solve for, ideally, well, normally you would say equals mass times the acceleration, but in this case I want to set that equal to 0 because we're interested in the maximum angle for which the block stays still, and that means 0 acceleration. Okay, if the angle gets any steeper, then this term gets bigger, this term gets smaller, and it will accelerate down, but the condition where it's just barely not accelerating is when this equals 0. Okay, and I can solve this expression, or I can simplify it. I can divide out the mg's that appear in both of those terms, and so I just have sine theta equals mu s cosine theta. That's what I've got from simplifying this, taking this to the right side. And so solving for theta, okay, divide both sides by cosine theta, so this becomes tangent theta, and then take the arctan. Right, let me just do that for you. Sine theta over cosine theta equals tangent of theta equals mu s then. And so theta is the arc whose tangent is mu s. Done. And you could do your quick checks and ask, well, what happens if mu s gets very small, you have very little static friction, and then theta gets very small too. Okay. And so this is actually the maximum angle that we have. I'll go ahead and label that max. That's what we're asked for. Okay. And then part C. Okay, so what happens if you exceed this maximum angle theta x? Well, if you do that, it accelerates down the plane. But what does that change in the work we've done so far? It doesn't change anything about this in the y direction, the fact that it accelerates down the plane. And the only thing that changes in our sums of the forces in the x direction is that now we'll have kinetic friction because it's sliding, and the acceleration won't be 0. It'll be a. So all I have to do is rewrite this expression for the sums of the forces in the x direction. It's now mg sine theta, and the mu s becomes a mu k mg cosine theta. Okay. And instead of being equal to 0, it's equal to mass times the acceleration. Okay. I can simplify this. Remember, I'm asked for the acceleration. Divide out all the m's. I don't need that. Notice g appears in both these terms, so I can write the acceleration as is g times these two terms. Sine theta minus mu k cosine theta. Done. That's part C. Part D adds a new twist. It says you have this mass here, and your angle is greater than theta max, so it wants to slide down the inclined plane, but you can, in fact, hold it in place by applying a pushing force perpendicular to the plane. Okay? And you're asked, well, for some theta greater than theta max, how hard do you have to push this block to keep it from sliding down the plane? And we don't have to redo all of our work. We can, from scratch, we can use the same concepts we had up above. We have to add another pushing force, another force to our free body diagram. Let me just here in dot dash because it's not in part A, but we need this for part D. Okay, and you could redraw the diagram if you want to, but we weren't asking you to do that for this exam. Okay, so now our sums of the forces in the y direction. We still have our n. We still have our minus mg cosine theta. But now we have a new one that's in the negative direction, minus p, and those have to be 0. So what this effectively does, or what it does, is it increases the normal force because you're pushing against the plane, basically, or pushing the block against the plane. So the normal force becomes mg cosine theta plus p. We're just adding plus p to our previous things. Okay, and then when we work out the force of friction, it'll be mu sn, or mu kn, times mu k times this term plus p. So let me do that. The sums of the forces in the x direction now will be mg sine theta, just like we had up above, minus the force of friction, which is mu s, or mu k, times n. I'm sorry, mu s, because we're holding it steady. Sorry about that. Trying to keep it from moving, so we have to switch back to mu s. So mu s times the normal force, and the normal force is mg cosine theta plus p. Okay, and we're trying to keep it from moving, so we're back to the situation where the acceleration is 0. Okay, so I put in 0 for the sums of the forces. And all you're asked to do here is to find this force P, and we could just solve for that. And let me write this expression out for you to show you the algebra in every step. So we have mg sine theta minus mu s mg cosine theta minus mu s times p. And so all I have to do is equal 0. Take p to the other side, or actually take these two terms to the other side and change the sign, however you want to think about it. So p will be equal to, now both of these terms have an mg in it, so I'll pull that out. Mg times sine theta over, I'll be dividing both sides by mu s, so this will be sine theta over mu s, and when I divide everything by mu s, this mu s goes away, okay, and I'll have a minus cosine theta. Done.